Okay, so today we will introduce the chapter 15, and this chapter is a little short, so we may finish earlier. Okay. So in this chapter, we will introduce the redox reactions, and also introduce the electrochemical cells, and we will show you about the batteries. Okay, before we introduced the main reactions, four kinds of main reactions. So one of them is redox reactions. Redox reaction. So I don't know how much do you still remember about redox reactions. So what's a redox reaction? What's a redox reaction?
Redox reaction that takes place when the transfer of electrons from the reducing atoms to the species.
So basically, redox reactions means there are some electrons moved from one compound or one reactant to another reactant, or from one element to another element. So this is called a redox reaction. Redox reaction. So in the last chapter, we introduced the spontaneous reaction, and also we learn how to determine the reaction is spontaneous or not. So basically, we can use the delta G, right? So what's delta G? Remember? Free energy. Okay, delta G. Okay, and so if the delta G, if the change of the free energy is more than zero, if the delta G is more than zero, so the reaction is spontaneous or not? It's more than zero. This means after the reaction, the free energy increase. Is spontaneous or not?
It's spontaneous.
Is it spontaneous?
Why is it?
No, it's not spontaneous.
Yeah, why is it?
The free energy should be less than zero. It means if the free energy decreases after the reaction, so this means the reaction is spontaneous. Okay. So we can use the spontaneous chemical reactions to produce electricity. Okay. So this is about the. Of course, this kind of reaction should be redox reactions, and these reactions are spontaneous. If they are spontaneous, so we can use these spontaneous redox reactions to produce electricity. Okay. So this is also about the electrical chemistry, chemical. For example, for this reaction, so the zinc react with copper, and here zinc is 0, and copper is 2 plus. So the electron will go from zinc to copper ion, and then to form zinc ion and copper element. Okay. So this reaction is a redox reaction because the electrons are transported from zinc to copper. And this reaction is also a spontaneous reaction. Because its delta G is less than 0. So we can use this reaction to produce electricity. So this is also about batteries. Battery. So battery can produce electricity, right?
Yes.
And what happens in battery is redox. They are redox reactions, like this kind of reactions. Okay. After this reaction, the chemical energy are changed to electric energy. Okay. And of course, there are many redox reactions. For example, in photosynthesis. What's photosynthesis? Photosynthesis means, so basically for reactions, we can provide heat, right? Provide heat. But photo is means we can just use the light, provide the energy from the light, use the light. Okay, so it's photo reactions. And the combustion with reaction. The compound react with oxygen, right? And of course, oxygen get electrons. Okay, and also some extraction of metals from ores, and also reactions in batteries, like this kind of reactions. Okay, so this is about the redox reactions, and we can use the spontaneous redox reactions to produce electricity. This is what happened in batteries. Okay. Okay. For example, this reaction, we can find the free energy of the substance. Okay. And this is the most stable element state, right? Most stable. So this is 0. Zinc solid is most stable state. So its energy formation is 0, and copper is 0. And this zinc GF, the formation energy of zinc iron is minus 147.06. The formation of copper iron is plus 65.49. So here we can see the formation energy, free energy of zinc iron is negative, but the copper is positive. So what does this mean? There are signs are opposite. One is positive, one is negative, another one is positive. What does this mean? This means if it's minus, so it's stable, then zinc or not. For example, the zinc iron, the delta GF is negative, so it's stable or not. Then zinc solid. Yes or no?
Yes.
Yes, yeah, it's more stable because it has low free energy. Okay. And the copper cation 2 plus, it has positive free energy. So it's stable or not stable than the copper. It's stable? Then no, it's not. It's not. So from left to right, we can calculate the free energy change of the reaction. So we can say delta GR reaction is minus 212.55. So what does this mean? This means this reaction is spontaneous or not?
Yeah.
Yeah, it's spontaneous. Okay? So it means it can happen by itself. Okay, we just put them together, they will react itself. Okay? So we can say the transfer of electrons can used to produce energy in the form of electricity. So after this process, after this reaction, the chemical energy converted to electrical energy. For example, we can like using this way for the reaction, okay? And the electron will move from zinc bar to copper bar. So the electron move from this side to this side, so it can produce electrical energy. And then we use the bulb in here, we can say it can light it, okay? Okay, now how to achieve this process, or how to convert the chemical energy to electrical energy? How to do? So basically, we use the electrical chemical cells. Okay, we can make the cells, and then we can achieve this conversion. So the energy released in a spontaneous redox reaction can be used to perform electrical work, and this is accomplished through it's called voltaic or galvanic cell. Okay, voltaic or galvanic cell. So this is a device in which the transfer of electrons takes place through an external pathway, rather than directly between the reactants. So basically, for reactions, the reaction happened directly between reactants. We just put the reactants together, right? Mix them together, so they can react. But for the design of electrons chemical cells, we can't mix the reactants together. We just spread them, and then we can achieve the electron transfer. So this process takes place through a standard pathway. Okay. So, for example, consider a spontaneous reaction that occurs when a stream of zinc is placed in a solution containing copper ion. So the reaction will take place like this. So the zinc bar will react with copper ion to form the copper solid and the zinc ion. So it's like, for example, we can do reaction like in this way. So in this way, the reactants are just mixed together. For example, this is zinc bar, okay, and this is copper solution. If we put zinc bar in the copper solution, this reaction will happen. So this means some copper solid will be produced. So on the zinc bar, we can see some copper solid. And the copper cation in solution will become the copper solid. So the blue color of the copper ion fades. And there are some zinc cation are produced in the solution. Some zinc go from the zinc bar to solution. Okay? So in this reaction, we can see the reactants are mixed together. Okay? So we can't get the electrical energy. You can't get the electric energy using this way, right? So basically, we can design a cell like this. Okay. So here we can see this side is zinc bar, okay, and this side is copper bar. It's copper, and in this solution, they are like a zinc nitrate solution. Okay, in this solution is copper nitrate, and then we can link these two bars. You say what? You said we can link them together, right? So and also we can use this like a salt bridge. We can introduce the salt bridge also link these two solutions. Okay, so in this cell, the electron will go from zinc bar to copper bar. So in zinc bar, in this side, the zinc lose electron, and then become the zinc cation. So this electron will not go into the solution. Okay, it will go from this line to this side, So to this side, so the copper cation will get the electron, and then will become this, will like deposited on the surface of the copper bar. So this reaction can happen spontaneously. So during the reaction, we can see the electrons are moved from this side to this side. So if the electron move, so here we can insert a bubble. So if the electron go through the bubble, so the bubble will be lighted. Okay. So this means the electron energy, the chemical energy changed to electric energy. So we can see in this cell, the zinc and the copper ion are no longer in directly contacted. They are not directly connected. We just separate them into two bottoms. Okay. So the reduction of the copper cation can occur only by a flow of electrons through a extended circuit. So namely the wire connecting the zinc solid and the copper solid streams. So the zinc and the copper streams are called electrodes. Okay. So any question for this process? So this reaction happened like the zinc lose electron to become zinc cation, and then the lost electrons are moved from this side to this side, okay? And then the copper cation in solution will get these electrons and then become the copper solid. So after reaction, we can see the electrons are transported from this side to this side. So because the electron move here, so here we can So it can light the bubble. You light a bubble, okay? So basically, the voltaic cell can be considered to be made up of two half cells. Two half cells. In each half cell, a half reaction takes place. This is one cell, right? And it can be separated to two half cells. So one is this side. This is one half cell. This is another half cell. Another half cell. Okay. So we can say in this side, so the zinc loses electron to form zinc cation. Okay. So this process is called the oxidation process. And in this half cell, so the copper cation get electrons to form copper solid. So this reaction is reduction reaction. Okay. Okay. So the electrode at which oxidation occurs is called the anode. So here zinc is the anode. Okay. The anode is electric. So the copper this side is called the cathode. Okay. So the copper is the cathode, and the cathode is positive. So the zinc metal is oxidized, and the electrons flow from the anode through the extended circuit to the cathode, where they are taken up in reduction of copper cation to copper solid. So this side is called the anode. This side is called the cathode, and the electron move from anode to cathode. Okay. So because after the reaction, because there are like zinc for this side, there are more and more zinc cation, right? Zinc cation. So this means the solution, the charge of the solution, there are more cations in this solution, and in this side, the copper cation changed to copper solid. So in this side, there are few cation. This side, there are more cation, but this side they have few cation. So we can use this. This is called salt bridge. To balance the charges of two sides. So for example, because there are two more cation this side, right? So in the solution there are sodium nitrate. The solution are sodium nitrate. So there are too much cation this side. So some sodium cation will go from this side to this side. Okay? And in this side, there are few cation. There are few cation, this means there are too much anion. Okay? So the nitrate anion will go from this side to this side. So using this way, we can say two sides are always neutral. Okay, because the solution must be neutral, right? If in this solution there are too much time, so some time will go from this side to this side. Okay, and if this side there are too much anions, so the nitrate ion will go from this side to this side. Okay, this bridge is called salt bridge. So through the salt bridge, we can balance the charges of these two sides. Okay. So any question for this? Hey, what are you talking? Okay, now question. What is the rule of the salt bridge in the cell? You or you? No. Definitely you too. Which one? Yeah. Hello? What's the rule of the salt bridge in the cell? What's the rule of the salt bridge?
Because they want to balance the charge.
Yes. Because after reaction, in the left side there are too much ions, and in the left side and the right side there are too much ions. So the solid bridge can balance the charge. Because through the solid bridge, the ions can move from left to right, and the anion will move from left to right. Okay, and then balance the charges to make the solution neutral. Okay. Okay. So basically, the solution, so the salt-bridge constant of a solution of an electrolyte like sodium nitrate, and will not react with the ions in the cells. Okay, so this is about the structure of the cells, the structures of the cells, and so here we how to write the electrochemical cells. So basically, we know there are two half cells. So we can write them like this, using this way to write using this way for the electrochemical cells. So here, this is anode, this side is cathode, and these two lines means salt bridge, and you also need to write out the states of the substance. Like this is solid, this is in solution, okay, and this side, this is in solution, this is solid. So basically, the anode is shown on the left, and the cathode on the right. And the single line separates the faces. Okay, the single line separates them. Okay, and the double dotted line indicates the salt bridge. So we can use this way to describe the formation of the cells. Okay. So any question for this? Okay. So here the electrolyte, electrode needn't always be involved in the redox reaction. It could be an insert substrate through which electrons flow into or out of. What does this mean? This means, for example, in here we can say the zinc is an anode, right? Is anode. The copper is cathode, and the zinc react in the the zinc is also a reactant, and the copper is also a reactant. So this means anode and the cathode are reactants, right? In this way. So, but basically, in fact, the anode or cathode needn't always be the reactants. We can like using it could be using these elements be the anode and the cathode, and the reaction happened in the solution. Okay. So for example, in this cell. So what does this mean? So this side is anode, right? This side is cathode. So here we can say this is iron 2 plus alcohol, 3 plus alcohol. So these are reactants. So both of them are in the solution, right? Both of them are in the solution. And this side, this is reactants or products, okay? And one is like gases, one is in solution. And the anode and the cathode is another metal. And this metal doesn't join the reaction. Okay. So in fact, in the cell reaction is this. Okay. But it's like look like here is not zinc, it's PT. The PT metal. Okay. This side is PT metal. This side is also PT metal. Just the reactants are in solution. And we can collect them, and the electron will also move from this side to this side. Okay. So this is like a PT is a very common metal to be used as anode or cathode. So can you give another example, another metal to be used as a cathode or anode? So basically, no, not.
Pardon?
So can you give me another example for an element it is used as cathode or anode, like a PT? So carbon. Yes, carbon. So basically, carbon also can be used as cathode or anode. So do you remember in the bottle, sometimes in the center there are a carbon, right? I remember when I was children, I just take it out and use the carbon to write something. I don't know what you do.
As a child, used to get carbon to write something.
Well, no, this carbon is like you see, it can also be used in the cathode. Because carbon, so basically, is very stable.
Are you talking about that coal-looking thing that's inside the battery? That's inside these triple A cells? Or
Yeah.
Yeah, is that more that line that's in the cell? Is that what you're talking about?
I don't know what you mean. so now here is just there are many other elements can be used as cathode and IPT. Okay, and remember carbon also can be used. The carbon, for example, the carbon basically is zero, so it's stable, so it can't, it's not active, so it can be used as a cathode. So the carbon doesn't react in the cells.
So same with graphite.
But
Graphite.
graphite, graphite is made by carbon. Yeah. Okay. So here because we can use another element as cathode or anode. Okay, so what's the driving force for electron flow in the cell? This means why the electrons can move from one reactant to another reactant, or why the reaction can happen. So basically, it's that by the affinity. The affinity of two electrodes for electrons is different. So do you remember affinity? We introduced this before, right? When we introduced the element table.
Yeah.
So the affinity means the is the ability of the element to attract the electrons. If its affinity is high, so this means it has strong ability to attract electron. So the difference between the affinity is like electron potential difference. So here we can say a table. The lithium. So for example, all elements can produce electron. In here, the ability of releasing electron is higher from bottom to top. Okay. So for the lithium, so this is the top one, right? So what does this mean? This means it is easy or not to give out electron. Easy or not? Yeah, easy. For lithium, it is very, very easy to give out electron. Okay? So have a short break.